Hello, I'm going to give a little lesson on section 2.1. It's about functions and graphs. So I like to think of a function as a kind of math formula, and it takes inputs and it gives you outputs. So for example, I've written down here the formula that turns Celsius into Fahrenheit. And so when we think of a function, what we think of is something that takes an input like Celsius, and then the output it spits out on the other side something in Fahrenheit. What I could do is I could take all of the Celsius and Fahrenheit and sort of pair them together, where in the first number I would write the Celsius, the temperature in Celsius, and then in the second number I would write the temperature in Fahrenheit. So in each of these mathematical objects that we call ordered pairs, the first object always represents the input and the second object always represents the output. In order for a function to be useful, it has to be consistent. For example, if you had some way to convert Celsius into Fahrenheit, and today 28 degrees Celsius corresponded with 82.4 degrees Fahrenheit, and then tomorrow 28 degrees Celsius corresponded with a much hotter temperature, it would be useless for you to use that function, right? It wouldn't do you any good, because if I told you what the temperature in Celsius was, you wouldn't always get the same answer. So what this means is that each input can have only one output, right? This is the situation that we are trying to avoid. And the problem with this is that when I started producing ordered pairs, I would produce an ordered pair 28, 82.4, and then I could also produce another pair of numbers that was 28, 97.5. So what's wrong with this is these are two of the same inputs that get paired with different outputs. So that's the thing that we're trying to rule out with this definition. A function is a set of ordered pairs, so it's like a little group like that, and each input has exactly one output. So you're not allowed to do this. You're not allowed to change your mind. So when we say the graph of a function, we just mean the same old thing that you're accustomed to, where you plot all the points and connect the dots, and that's what makes the graph of a function. So if you took all of these ordered pairs and you plotted them, then that would make the graph of a function. And the way it works is I like to put the inputs on the horizontal axis, and then if you go up till you hit the graph, then this will tell you which output corresponds to that input. So right here is the pair 28 degrees Celsius and 82.4 degrees Fahrenheit. This topic of domain and range, students always seem to have difficulty wrapping their minds around. There's just something about it that sort of seems like, okay, I understand what you're saying, but I don't understand why. So I hear that, and if you feel that way, you always felt like, what's the point of this domain and range business, then, you're not alone. That's normal. A lot of people feel that way. So the idea is that all of the possible things that you could put into this function are the domain, and all of the possible things that you could get out of the function are the range. So in our example, all of the possible degrees Celsius would be the domain, and the set of all possible degrees Fahrenheit would be the range. So you can actually just kind of read the domain and range off of the graph. So I have a kind of sort of smooth graph that has an open endpoint at one side and a closed endpoint at the other side. It does go through this little point down there at the bottom. And let's just look at this graph and see if we can kind of tell what the domain and range are. What I do is I imagine kind of smashing the graph down this way and smashing the graph down this way. So the inputs go on the horizontal axis. So if I want to smash the graph this way, then I'm looking for the domain. So let's just do that. Let's just look what happens if I just kind of compress everything down onto the horizontal axis here. Then what parts of this would actually get a graph that touches it? So all of these pieces right here are the part of the horizontal axis that would get hit if I sort of smashed it down this way. And then this endpoint right there is a closed circle, so I'm going to use a bracket on this side. And this endpoint over here is an open circle, so I'm going to use a parentheses on this side. So I intended all of these scales to be 1. So that's it. We can just now look at this and look at the part that we've shaded and just use that to just write down what the domain is. So all the way over here on the left, 1, 2, 3, 4. I'm looking at -4 on the left side. And then over here on the right side, 1, 2, 3, 4, 5. It goes up to 5 on the right side. And it's a bracket because of that closed circle right there. The parentheses on the left side, I know I said this, but that's that open circle over there. All right, let's repeat this, but now we're looking for the range, so that's all the possible outputs, which means I am going to try to smash things onto the vertical axis. This axis right here is the outputs. So let's just sort of compress the whole graph and see which parts of this axis do actually get hit here. And when I look at this, I'm looking at a bracket, because this piece right here, and then all the way down, all of this gets used right there, right? And this piece is also a bracket because it's a closed dot. It does actually go through that point. So for this range, there's some symmetry in the numbers. These aren't perfect, but the bottom point, 1, 2, 3, is going to be 1, 2, 3. This is going to be a bracket at -3, and then this one's going to go up to 1, 2, 3, 4. It goes up to +4 up there. So that's my kind of visual method for determining the domain and the range. I kind of imagine smashing it onto the two axes and then seeing which part of the axis gets used. So every time you've written down an equation before, a function is what was going on behind the scenes. Well, potentially a function was what was going on behind the scenes. So we're going to try to look at some equations that we're kind of familiar with and see if it makes sense for y to be a function of x. And when you use that language, is something a function of something else, what you're saying is the output a function of the input. That's the way the language works. So if I look at this first equation here and I try to make it look like a function, which means I want to write it like output equals, then I would add 2x to both sides. So I would get 2x, I'd add 2x squared to both sides. I get 2x plus 5. And so there I've done it. I've tried to write it as though y is the output and x is the input. So let me see. I'm going to try to do that same thing down here with example B, and let's look how that goes. So I'm going to add 2x to both sides, and I'll get y squared equals 2x plus 17. And now here's the thing. Remember, when you square root both sides, you got to put a plus or minus in front. Okay. So if you just look at this formula right here, if I plugged in a number like x equals 0, then I would get an output like y equals 5. So every time I plug in one number, I would just get one output. But what would happen? What happens if I plug in x equals 0 to this equation? Then I would get y equals plus or minus the square root of 17, which means y could be 17. Y could be the square root of 17, or y could be the negative square root of 17. So there's two possible choices for y. Remember, a function can't change its mind. Every time you pick an x, you need to get the same y out. So that happened in this example because when I pick an x, I'm always just going to get one y, but you can see this plus or minus right there means when I pick an x, I get two y's out. So this first example is a function, and this second example here, b, is not a function. How can you tell? That's how you can tell if you're trying to figure out if y is a function of x and you have an equation, you can just solve for y and see if you end up with one y or with multiple y's. The vertical line test is a way to do this. It's a way to test, is y a function of x? The way it works is you draw all the possible vertical lines, and the graph passes the test if all of those vertical lines only hit the graph one time or less. And it fails the test. If you can draw a vertical line and it hits the graph more than once, then the graph fails, and it is not a function. So here's a couple of example graphs, and what I'm going to try to do is draw a bunch of, and you don't have to actually draw the lines, but in your mind, draw a bunch of lines and see where those vertical lines hit the graph. So as I draw these vertical lines on the first graph there, I'm only hitting it one time. But you can see if I try to do that same thing, I'm drawing all possible vertical lines, and then this graph fails because I get 3 hits right there, right? So, right here, there would be 2, right? There's one right there, and there's one right there. So the first graph passes and means y is a function of x, and the second graph fails and means y is not a function of x. Again, the way it works is you draw all the possible vertical lines. If you just hit the graph once, then it passes and you are a function. But if you can ever hit the graph more than once, then it fails and y is not a function of x. So we're going to have new notation when we write functions. We used to write equations where we had y and x, and we were thinking of y as being the output and x as being the input. And now we're going to change that up. Instead of writing y, we're going to write f of x. So y is equal to f of x. There isn't a different thing. There isn't a different meaning. And there's a simple reason why it's better. You can see if I make a choice like x equals 1, then when I plug that in, I would have y is 1 squared plus 3, so I would get y equals 4. So that's fine, but you can see I've got to make sure that I write down what the x was that I plugged in. And if I get rid of that information, then it's hard for me to tell, right? If I just write y equals 4, well, what was the x that you used for that? But in function notation, if I keep track of the input, that's where the input goes right there. So I can write the same piece of information in a simple, more compact way. I'm just going to write f, and then where I used to put x, because I'm plugging in x equals 1, I'm just going to put a 1 there. And that way you know, right? If I write something like this, f of 0 equals 3, now you know just by looking at the notation that I used what the x value was. So that's what's better about function notation than just regular old y equals notation. I don't need like a separate line or some other way to indicate what the x was that I used. It's just this is the input right there, right? And you can do this with anything you want. It doesn't just have to be with numbers. If you want to, you could write f of a equals a squared plus 3, or f of smiley face equals smiley face squared plus 3, right? Anything that you want. That's the idea behind function notation, is I keep track of what I plugged in right there. Okay, this idea is simple enough, but this problem kind of comes back later, and so I just want to take a minute just to focus on this pattern and what happens when you're asked to evaluate f of negative x. So what that means is I just need to take this negative x and plug it in for all of the x's in the equation. And the tip that I have is to make sure that you use parentheses when you do this. It just kind of makes it easier visually to see what's really happening. So remember, let's look at these powers. That's what I want to, that's the pattern that I want to try to see. Remember, like a positive times a positive is a positive. And then let's look at these powers. That's the pattern that I kind of want to see what's happening there. So remember, a negative times a negative is a positive. And then if you do this one, you'd have a negative times a negative times a negative. So The first two negatives would make it positive, and then I would again get a negative. And then with the fourth power, it'd be like negative, 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 right? The four total, they're all just going to cancel out, and that's going to end up positive again. So when I simplify this, these even powers are just going to eliminate the negatives, but the odd powers right there, because that's a 3, they will change the signs. Now this sign, I'm just going to keep it because 2 is even, right? So 5x squared. Now, this is technically negative x to the power of 1, which is odd. So I'm going to change that one. And then this number there at the end, it doesn't have any x's in him, so he remains unchanged. So the pattern there is the even powers will annihilate the negatives, but the odd powers will change the sign of the coefficient in front of them. Okay, so this is the last problem on the homework, and I want to just kind of, cut you guys some slack and just work through a specific example. And also this problem kind of brings it all together, we get to do all the parts. So they give us this graph and they ask us to figure out the function's domain, range, any of the intercepts, and then this value f of -1. Okay, so let's have a look at this function and see how it goes. So the first thing is the domain. So for the domain, we compress everything down onto the x-axis. So I'm not using any part of this, right? There's no function here. So I'm not using any part of that x-axis. So there's nothing to compress there. And the same thing with this piece over here, right? If I compress the function down, there wouldn't be any function over there. So it's just this little piece right there. That's the only part that gets used, and then there's a bracket on the right-hand side because of that closed circle, and a parentheses on the left-hand side because of that open circle there. So, so what did we get? Oh, write down the answer first. So this is what I get. So this goes over to 1, 2, 3. So this is going to be -3 to 0, and I have a bracket on the left-hand side and a parentheses on the right-hand side. Okay. Now for the range, let's have a look at that. So now I'm compressing the graph this way, right? So it's going to be all these pieces right here, and then I have a parentheses on this side and a bracket on that side because of the close and open circle. So for the range, I'm getting the range is going to be the interval from bracket, that looks like -4 to me, -4 up to 5 with a parentheses there. Okay, now they're looking for the x-intercept. So I do see an x-intercept. There it is right there. And the way that MyMathLab wants the answers, I know that a lot of students are kind of trained to put intercepts as an ordered pair. But all this MyMathLab wants is the x value. So as I look at this picture right here, the x-intercept is at -2. And the y-intercept, when I look for a y-intercept, oh, there he is right there. So all they want is the y value of these intercepts. So they want the x value of the x-intercept and the y value of the y-intercept. So 1, 2, 3, 4, so -4 there. And then find the indicated value of the function. Okay, so f of -1. So this means here is x equals -1, and now I just need to start searching for the function. I see the function below, so I'm just going to go down till I hit the function, and then I'm going to use the vertical axis there to try to read off the y value. So -1, 2, 3. So there's the y value at -3. So according to this picture, as I read it, f of -1 equals -3. Okay. See you guys.